Greetings, friends. I'm looking at AN672 from Intel, and I'm going to explain some of the points made in this application note, and I'm going to use this in conjunction with a free piece of software called Saturn PCB Design. Okay, top one here just first starts looking at the different ways that the high-speed link can go. It can go from board to board, chip to chip, chip to module. Okay, we're now talking about the dielectric constant and the weave and the copper finish. Okay, so if one looks at it, you have two lines. One line is your reference, and one line is your signal, which goes above the left reference on a single-ended, talking single-ended. Okay, these two can be seen as two plates of a capacitor, and the capacitor between the two, the amount of capacitance between these two plates will give you loss. The higher the capacitance, the more your lines are going to be attenuated. On a very basic level, the longer the lines, the higher the impedance of the lines. Okay. So over here we're looking at the absorption, which would be the attenuation. Attenuation is showing it between different types of PCB materials. Okay, I'm gonna swap over now to Saturn PCB, and we can see it in Saturn PCB. We can see that your width of your trace is the width of the plate, which I'm defining as, at this point in time, as a capacitor. I'm using simple terms to keep things very simple. Okay, it's a complex topic. I want to keep it simple. Okay, so we're looking at this this drawing, and you've got one plate which is your reference or your ground plane, and one plate which is going to be your signal. The two will create a capacitor, and the amount of capacitance is going to affect the signal as it goes down the line. Okay, I'm keeping it just to capacitance without inductance on a very simple level that most people can understand. Okay. The concept I'm going to speak about now is characteristic impedance. Now, we talk about a 50 ohm characteristic impedance line. Why 50? Because everyone works on 50. Okay, we're looking at the characteristic impedance now at this point in time is 81 ohms should I go down to from 9 mils to 8 mils on the stack up for H, and I go solve, it comes down to 77. If I go to a 6 mil trace, it also goes up. If I go to, say, to a 10 mil trace, I'm roughly at 58 ohms. Okay, I'm now going to describe why on a two-layer PCB it is very, very difficult to have a characteristic impedance. Okay, I'm now going to change from 8 mils to 60 mils. Why have I changed from 8 mils to 60 mils? 60 mils is 1.6 millimeters. I use mils for the I change between mils and millimeters depending on what I'm doing, but for this I'm using mils, imperials, thousandths of an inch. So 60 thousandths of an inch is 1.6 millimeters. 1.6 millimeters is your average run-of-the-mill PCB that you're going to get from seed or from JLC PCB. Okay. Now remember, 90% of the time you are going to want 50 ohms. Okay. A 10 mil trace is 126 ohms. Shall we say we're going to a 40 mil trace? A 40 mil trace is a 1 millimeter trace. Shall we say I'm going to an 80 mil, I'm purposely jumping with big numbers. An 80 mil trace. 80 mil trace is 60 ohms. A 90 mil trace is 56 ohms. Okay. Hundred mil trace is 53 ohms. Okay. Now, let's assume that you want to create a 50 ohm trace on a standard 2-layer board. In order to keep 50 ohms, you're going to need that your output is going from your RF to the antenna at 100 mils. 100 mils is 2.5 millimeters. And 2.5 millimeters, there's no ways that you can do this on a 2-layer board, especially not with surface mount. There's no ways of getting a 100 mil trace connected to a surface mount package. Not any that I know. Okay. So now one can start to understand why when you buy modules, RF modules, very often they are not put onto the main PCB and they are left as RF modules, be it ESP, be it NRF. When you buy a module, they generally are on small module boards, and generally people do not incorporate them into the main PCB, because I'm going to show you now why. We're going to go back to a 10mm trace, and instead of a 1.6mm PCB, we are going to move to a 30mm PCB. A 30mm PCB even a 15mm PCB. A 15mm PCB with a 6mm with a 6mm 12 mils. $14. $16. Okay, it's still difficult to do it even on a thinner PCB, but one can see that it's a possible. You can possibly get a 50 ohm PCB using a thinner PCB. There are different options also. This is if you're going to have the line internally within the PCB, within the stack up. If you're going to have a strip line. Okay. A practical way of doing it, of creating a 50 ohm on a 2-layer PCB, would be a coplanar wave, where you have not only your height playing your height here, your width, but you have the gap between your reference layers. If you're going to have you're going to have a bottom reference layer, your signal layer, and on both sides of the signal layer you're going to have two guard tracks. These guard tracks are going to create the 50 ohm. So for example, now if I went down to a 6 ohm guard, or a 4 mil guard, I'm already at 52. I'm already at a 52 ohms. The problem with this is that you have undercut, which means that when your PCB is etched, and it's not a straight line. You don't etch straight, you etch with undercut. And you'll have undercut where it's actually the opposite way it's shown here. This over here is shown that this would be wider. I personally think it'll be the other way. I think that you will have undercut. That as your etchant goes down, it's going to cut out. And especially if you are playing at the level of 1 mil difference, shall we say, if I have 3 mils between my traces, I'm exactly at 40 mil. I'm at 40 ohms, 49 ohms. If I go 1 mil away, 1 mil change has already changed the characteristic impedance. It is very, very critical. Okay. That is very, very high level, very simple. Why you don't want to make it two layer PCB, which needs to be 50 ohms. Okay. What else did I want to explain here? Okay. I wanted to explain something else also. We'll go back to the microstrip. Okay. The microstrip, I wanted to explain something else. Okay. I explained now what characteristic impedance is. I want to explain now TPD. TPD is the speed that information travels down copper. Okay, which is in most low speed applications not critical. Okay, and I want to start off with looking at this. TPD, and we're going to take FR4, simple FR4, and one can see I'm at 150 picoseconds per inch. Okay. If I go to half an ounce, 1 ounce, 2 ounce, doesn't change that much. Less than 1 picosecond per inch. Okay, but let's take this now. This is with air outside, and my connector is on the outside. I'm now going to go and put that connector inside, and now one can see that I was at 150 picoseconds per inch. I have gone now to 181 picoseconds per inch. Okay, complaining to me about connector width. Let's take this down to 10. Okay. Okay. One can see that even if I change the width of the connector, I'm still at 181 picoseconds per inch. Okay. This is a very important point. Okay. Every PCB joker can tell you that when routing to a DDR data lines, that one needs to keep the length the same. Okay, and I've seen one or two times people who are old school PCB people, and they come and they measure the traces on all the layers, and they say, you see, I'm perfect. All my lengths match. But what they don't realize is that each layer is going to have a slightly different TPD, which means the delay caused via the track. Okay, so if I've routed on an extreme case, I've routed D0 on a top layer, and I've routed D1 on a middle layer. Okay, and I've kept the lengths exactly the same. The problem will be that the layer, the D0, which was an outer layer, is going to get to the RAM chip before the data gets to the RAM chip on the internal layer. Why? Because of your delay per minute per inch. Assuming I've kept the same length, kept the same length. So it's not enough to keep the same length. One needs to keep the same length per layer. Okay. Robert Ferrarek from Federal Academy made a few videos a couple of years ago where he created an Excel sheet where he works out all the delays in Altium 20. I believe it is done automatically. Okay, I want to at this point in time talk about lengths and vias. Okay, so you want to keep your length correct going from your controller to your DDR chip. And what you want to do on top of this is you want to keep the delays correct. Now let's make the assumption that you at some point in time in your life, in the lifespan of your product, need to change PCB manufacturers. And the PCB manufacturers that you're changing to are unable to create your original stack up. So as they're unable to create the original stack up, your stack up is changed, which means that your length of your vias have changed. The signal path lengths have changed. Okay, and on high speed DDR, just the change of your of the via can affect you. So the advice that Robert had was to try and route all your data groups on the same layer pairs, so that if you change your stack up, your layer pairs will be adjusted accordingly. You're not going to have D0 and D1 because of a stack up change having a different delay from controller to memory chip. Okay, I have wandered slightly away from what I wanted to talk about. I did not want to talk about DDR. I wanted to talk about Sredis. But however, okay. Yeah, I've shown. Here he shows the Here he shows the. Here the person shows the difference between the delay times of the same differential impedance using two different types of materials. One can see he's talking about capacitance. When I spoke about it being capacitance per inch, one can understand that your capacitance is at this point is the way that you are attenuated because of capacitance. On a very simple level, he's taken two differential pairs, and one can see that there's a very big time difference in picoseconds. A very big time difference in picoseconds. This is not going to bite you unless you are going to very, very high speed circuits. Okay. The next discussion is to do with FR4. Okay. PCB material is basically woven fiberglass. Okay. And your fiberglass has different electric properties, whether you are over the weave or whether you're over the glue. Okay, I don't want to go into exact what fiberglass is. So the tighter ones weave, the more consistent the impedance will be over the PCB. Okay, cheaper FR4 has more weave. Okay, as we're looking at this, I'm going to describe something else. One can see this weave over here is called 106. So if I have a trace which is going over weave and not over air or not over glue, it will have a different characteristic impedance. Okay, at high speed, the weave begins, the type of material, the type of weave used has an effect. How much is of the resin, or whether I'm over the mesh or the resin. Side issue which I saw on this, which is something I picked up from Bill Hurd from Hackaday, is a cheap way of getting around this is to offset your PCB by 10-15 degrees. So if you're going to have basically most times your tracks are going to be running either horizontal or vertical. So if my PCB is made and have an angular twist from the weave, I've taken it and I've given it a 45 degree twist, which means my lines are not going to be going straight across. They're going to be going they're going to be going along. They won't be going only along the mesh. They'll also be going over the resin. Okay, the higher quality the PCB, the tighter the mesh. Okay. Here he is going into an example and he's showing why zigzag routing might be better. For example, this top trace is going to have a different impedance here to the bottom trace. Not only is the copper, is the weave a problem, also the copper surface finish. The copper surface finish can also have an effect. The skin effect, I don't want to go into it. Okay. We're now talking about I'm not talking about a different concept. I'm talking about crosstalk, or one can call it coupling. Okay, on a single-ended communication line, one wants to avoid coupling, which is noise, which is caused by two parallel lines running down in copper, close proximity one to the other. Okay, one will see this as the aggressor and the victim. Okay, once again, one can go into changing these parameters and changing how much crosstalk one has, whether the crosstalk is between two lines, two single lines, two differential lines. This is more two differential lines. This is a differential pair, this is a differential pair. This is the aggressor, this is the victim. Okay. Okay. Here is one stack up construction. Okay. At the moment, we're looking at a BGA device. And the way they've drawn the BGA device is they've put a veer. These are veers which would have a dog tag, which means you can have your ball. The ball is going to come down onto the pad. And from the pad, you're going to go away into the middle between the pads and create a veer. Okay, this is one can see here the veer and your trace design. Okay. This type of fan out is only practical on relatively large BGAs, because the smaller the BGA gets, the less space you have between the pads, and the less space you have between pads, sometimes you're not going to have play space to put in a veer. Okay. Here they're talking about differential pairs which are going out, and they're separated by a ground plane. So you're going to have two pairs, your plus and minus on one layer. Below that you're going to have a ground layer, and below that you're going to have a third layer where the second differential pairs are leaving. Okay, so one can see over here the way it's drawn, that you've got your first two, second two, third two, and fourth pair. Okay. These are very high speed. These are very high speed traces. Not something that I've personally done before, and one also needs to make the assumption that you can have spaces to have two traces going out between your veers, which is a relatively expensive PCB. Okay. Yeah, he's talking about using formal clearance, and he's talking about basically a 1mm BGA. 1mm BGA, I'm talking about 1mm pitch ball to ball. You're not going to be able to do this on a 0.4mm, 0.6mm BGA. You're not going to have the space to go between the pins. Your veers won't allow you to do this. Okay. Okay. At the moment now, we haven't spoken about resistance. Okay, we're talking about your capacitance loss. And your capacitance loss across the track as the track goes down from your source to your node. But one must also realize that copper has a resistance. And as copper has a resistance, you're going to have resistive losses down this track also. So here we're talking about comparisons between 4mm, 5mm and 6mm traces. Attenuation in dB. And one can see the attenuation in dB going up as you use thinner tracks. Okay. Personally, I don't think that I've ever got above 1 megahertz in any design that I've looked at. Very rare, and this would be a big issue if you're talking about a 28 gigahertz line. A 28 gigahertz line would be somewhere down over here. Okay, and this would be your losses. Okay. One can note that the graph stops at 30 gigahertz. That's roughly where the end of that we get to on Serdis. Serdis, as far as I know, tops out at a 28 gigahertz. The highest, fastest Serdis which we have. Okay, but you can say to me, Arya, but we have a 56 megahertz Serdis. A 56 megahertz Serdis is something which is used PAM4. Okay, PAM4 is basically you've split up your levels into 3 different separate levels. So you're still on a 28 gigahertz physical layer, but you're using level separation. Okay, basically in a similar way that you are able to store more than one bit of information per cell. Okay, I don't want to go into it. Okay. Loosely and tightly coupled traces. Okay. Okay. Loosely and tightly coupled traces goes into an area which I first need to describe. True differential versus Serdis. Okay, your true differential system is like a twisted pair cable. on a twisted pair cable, your label, your return is on the opposite pair. Okay, old school telephone networks, transformers, differential pairs were true differential pairs. Okay, now we call them differential pairs. We call them differential pairs, serdis high speed, but in real terms they are not differential pairs, because what actually happens is the return current is mainly on the ground plane and less between the two connectors. It is closer to describe serdis as two separate differential pairs than differential pairs where the one is the return of the other. Okay, so this gets into the term of loosely linked differential pairs. If I have my differential pairs very, very close to each other, or I separate them away, that is loosely differential pairs. The common wisdom today is to loosely couple differential pairs. Okay. I've just basically described what is loose versus tight differential pairs. Okay. Differential pairs, in theory, at the same point in time, your edge needs to go down the wire from your source to your end node. Okay, and your edge is what you want to get to your end node without, at the same time, your differential pairs. So you have skew differences between your positive and your negative side of the differential pair. Okay, and you're going to have these meanders to keep your differential pair so that the edge goes down the line at the same point in time. You don't want to be a difference between where the edge is. Okay. Once again, this graph is showing. This table is showing the dielectric constant, the trace width, and how they've changed the height. The height, these two are a pair and these two are a pair. They basically want 100 ohm differential pairs, and they've changed the trace separation. Okay. 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 Any two parallel lines, any two wires that go together for an extended period of length, they will be coupled between your active line and your passive line. Now, your active line we will call the aggressor, and the passive line we'll call victim. Now, as it goes down the line, as we go down the line, we have inductive coupling. And your inductive coupling is going to induce a voltage in your victim. Now, near end and far end, your far end is generally a high impedance input, and your input is generally higher, and your output is a low impedance. So the voltage will be induced in the trace. We're going to have a voltage induced in the trace, and your voltage is going to separate in both directions. One towards the receiver and one towards the transmitter, your TX, your transmitter. Okay, this is near end and far end, edge coupling. Okay, I don't want to go overly into detail of this. Okay. Okay. We're now talking about broadside coupling. Okay. Broadside coupling, I'm showing this example, and I'm going to explain that we have two differential pairs, and the two differential pairs are one above each other. And here there's a height difference between the pairs. So this differential pair is going to affect this differential pair. Depending on how your stack up is built, depending on how much it's going to do it. To be noted here is you have ground, signal, ground. In many cases, one can make this H smaller. By making H smaller, you are increasing your coupling to ground. By increasing your coupling to ground, you are reducing the effect of the next layer up. Okay. Which means one can look at the stack up. I have not done it, but I'm saying one mitigation is to reduce H, and this H over here, and to make it closer. Okay. Okay. The way they show to do it is to separate. Instead of having the layers, the pairs going on top of each other, to separate them out. Okay. Not always possible, nice to have. Here is an example of them doing this. For example, one can do it the way we described on top. The way we described it on top, we had here we had a ground between the layers. If we have a ground between the layers, then we don't get to this problem. This problem is caused if you didn't have if you had a separate ground layer here, you wouldn't get to the issue. Okay, but the way it's described now, they're saying to separate the traces. Okay, here's an example of the way they've routed it. Okay. I'm now gonna talk about transparent via design. Okay. This is a TDR, which is a time domain measurement, which sends out a pulse, and the pulse will go down the line, hit the end of the pulse, end of the line, and echo back. This is basically what TDR is. Okay. So if I'm going to talk about a via, let me see if I've got a via. Okay. And I have a trace on the top layer that I want to move to a middle layer. So from my top layer, I have a via that comes down and goes to the middle layer. Now, as long as the trace is moving on the top layer, this trace has a reference layer below it. And assuming my internal layer also has the same impedance, I want to create a via from top to middle. From top to middle, my via, the stub of the via that goes between the top and the middle, that point in time, that point on the PCB, I don't have a reference layer next to, no reference layer mills away from the via. Via is a hole going through. Okay, so that is what they're showing here on this plot. They are showing here on the plot what happens when I go from one layer to another layer using a via. And using a via, you can see I'm at 100 ohms, and the via is suddenly at 80 ohms. This is the anomaly which one wants to try and minimize. Okay. They're showing it from, don't want to go into too much detail about this. Without saying that if you are in a higher speed design which requires this, the way to get around this is to put vias to ground around your via, which goes from stitching vias around your via for the signal. One needs to realize that there are limitations of doing that. You can't put hole to hole. You can't put a via right next to it. You have to have some type of hole to hole separation. But that is the mitigation. Okay. Okay. Not sure if this is what they're talking about. Block DC optimization. Okay. Okay, talking about putting cutouts underneath capacitors. I'm not overly up to why they were doing this, and I don't want to get into this point. Okay, connector optimization. There are certain connectors which you're gonna use for differential pairs, and it's showing that one that takes the pair is not arbitrary. One doesn't use arbitrary. They more than likely have put a ground between your differential pairs. Okay. And I've basically gone over on a very high level what was described in this application note. Besides the point of blocking capacitors, it was all known to me. As I'm still looking for work. Okay, it's probably a good thing for me to go over high-speed design like this. Okay, thank you for your time.